Hello, we are continuing with part 2 of intermolecular forces. Intermolecular forces continue to have a large effect, particularly on liquids where there's still some motion in atoms or molecules between them. So in liquids, the greater the attraction between molecules, the more slowly it will flow. Viscosity is the measure of a liquid's resistance to flow. So have you ever tried using ketchup before and getting it out of the bottle? Cheaper ketchups contain more water and are less viscous than the more expensive brands. Not vicious, it's not attack ketchup. It is viscous. The thicker the ketchup, the harder it is to get out of the bottle, the more viscous it is. Intermolecular forces also have a strong effect on the surface of liquids. These strong forces can pull the molecules in the liquid closer together, making them denser on the surface, causing increased surface tension. This allows water striders, those little water bugs, to walk on water. They walk on the surface of the water because of the water tension. And there's a cute little picture. You could see his feet kind of resting on the surface of the water without breaking through. As you know, snowflakes are a solid, and you can imagine that those hydrogen bonds must have something to do with their shapes, and they do. However, let's talk about phase changes when things change from solid to liquid to gas, because they always involve energy. So as energy is added to any system, molecules end up moving faster. Let's take a look at the heating curve of water. Remember this: if I took a chunk of ice and stuck it on a burner or a hot plate and just kept it going, the thermometer wouldn't look like you would think it would look. At first, the temperature of ice rises as energy is added to the system, and you can see it's going from -20 to 0. When it hits 0, then the temperature on the thermometer, if you stuck a thermometer in this chunk of ice, would stop changing. At first, the temperature of the ice, the molecules are moving, the temperature rises. Now the energy is being used to change states from solid to liquid. The thermometer's temperature does not rise. And you can see by the blue bar what is happening. You haven't stopped adding energy in. You're still adding energy. It's just that the thermometer is not registering that change because the energy is being used to change state. Once it all hits water, once the container is now all water, the temperature of the water will rise again. So this section here is the temp of water rises as energy is added for that red diagonal line. Once all the water hits 100 degrees, now it has to change state again. It has to become a gas. The energy that you're putting in is being used to change that from a liquid to a gas state. So the temperature on the thermometer does not change, does not rise. And you can see that here on the blue horizontal bar. Once all the water has changed to steam and there's no more water left in the container, now the temperature starts to rise again. Continues to rise as energy is added, and that is the last state. So if you take a look at this, there are 2 times where temperature does not change, when it's changing state or changing phase. All right, we're going to do an example. Find the change in an enthalpy, delta H, when you have 1.5 moles of ice at -25 degrees Celsius to water vapor at 125 degrees Celsius. I'm going to give you some numbers that you need. The specific heat of ice, the specific heat of water, because it's different to raise 1 gram 1 degree, how much energy you need, the specific heat of steam, and the delta H for fusion and evaporation or vaporization. Please note one is in kilojoules, one's in joules, and one is measured per mole and one is measured per gram. So you'll have to make some adjustments in your equations. Remember, during melting or evaporation, or if we were going in reverse, condensation or freezing, the enthalpy unit does not require a change in temp, delta T, since the energy going into the system is being completely used to change the phase. The thermometer's temp is not rising. All right, let's look at step 1, and I'm just going to do the first 2 steps. Calculate the heat required to change 1.5 moles of ice at negative 25 degrees to 0 degrees Celsius. The equation is Q equals mc delta T. Remember, Q is always an energy that's going to be joules or kilojoules. M is mass times specific heat, that's C, times the change in temperature. So in this one, 1.5 moles we can change to 27.0 grams of ice and set up the equation. So Q equals 27 grams times the specific heat of ice times delta T, which was 25 degrees. It's going from negative 25 to 0. And do the math. And Q for the first step is 1410.8 joules. Second step, we have to figure out how much energy was required to take it all from ice to liquid water. There's no temperature change, so that doesn't have to be part of the equation. So Q equals M times delta H of fusion for this. So since this unit is in moles, we don't have to use grams. We could just simply use the 1.5 moles. So plug it in. And Q equals 9.015 kilojoules. No, one's in joules, one's in kilojoules. You'll have to adjust at the end. Now you continue by determining the remaining steps. You have to go water at 0 to water at 100 degrees, water from 100 degrees Celsius to steam at 100 degrees Celsius, and steam from 100 degrees Celsius to 125 degrees Celsius. Final answer, in a moment you can pause and work it all out, then come back. And the final answer is shown below. This is the end of part 2.